Hi and welcome to this video. In this video I'm going to continue taking a look at chapter 7 of Richard Dedekind's essay, The Nature and Meaning of Numbers. So in the last video I got all the way up to theorem 97 in chapter 7, and so we're going to be starting this video off with definition 98. As usual, I'm going to bring up on the screen, I'm going to read through the contents of the chapter, and I'm going to bring up on the screen the part of the chapter that I'm talking about, and I'm going to be stopping off and giving my interpretations and explanations about what Dedekind is talking about, at least my interpretation to the best of my ability. So let's jump straight into it with this video. So actually, before I start, there's a couple of points that I had a couple of brain farts in the last video. Theorem 94, I think it was, which I don't actually have it here on the computer. So theorem 94, there was one of the inequalities that I couldn't quite figure out for whatever reason. In the moment, it was just something that I couldn't seem to figure it out. So theorem 94 states that each of the conditions n primed less than or equal to n, or is at most equal to n, should I say. n primed is less than n primed, and m is less than n. These are all equivalent. Okay, so this is theorem 94. So I'm just going to clarify this before I move on. So the proof follows immediately from 93. So 93. In 93, replacing the m of theorem 93 with m primed gives the first two the first two forms, the first two inequalities, and then from mu in 90, evidently we get this, and we do, because from 93, again, replacing m with m primed, we see that each of these is in turn equivalent to the chain of n being part of the chain of m naught primed. Well, that is exactly what mu says from theorem 90. That is equivalent to m is less than n. So that's theorem 90 that says that. So both of these, the equivalence of these two comes from theorem 93. This also comes from theorem 93, but then we need to use theorem 90 to get the m is less than n. So I just wanted to clear that up. There was also theorem 97, which I went through the first part. The proof of theorem 97 follows from 74 and 93, but then there's another Dedekind suggests another possible way that we can prove theorem 97, which is using theorem 96, and it does follow immediately. Again, there was just a little blip that I had. I couldn't, maybe I was getting a little bit tired by that point, and I couldn't quite see what I needed to see, but yeah, it does follow immediately. I just couldn't convince myself that it did. Okay, so let's get on with definition 98. So there's quite a lot to get through in this video. I expect it is going to take quite a... this video could be quite a long video, but I'm going to go into as much detail as I can, as with all my my other videos, really. So definition 98, if n is any number, then we will denote by Zn the system of all numbers that are not greater than n. Okay, so system of numbers that are not greater than n, and hence not contained in n naught primed or n prime naught, whichever you prefer. So in other words, Zn contains all numbers, and therefore must be a part of n, because remember, uppercase n is the system of all numbers. Okay, so Zn contains all numbers that are not greater than n. In other words, Dedekind doesn't use the term less than or equal to. He tends to use not greater than, or at most equal to. But I think I can be forgiven for saying less than or equal to from time to time. And hence not contained in n0 primed. So n0 primed, so we've effectively got all of the numbers from 1 up to n, and then we've got n primed, and then all of the numbers after that. So n0 primed contains all of these numbers. So I can't remember which theorem it is that says that n is not contained in theorem 82. In the transform chain, n0 primed of a number n is contained its transform n primed, but not the number n itself. So n0 primed contains all of the numbers n primed onwards, and Zn contains all of the numbers from 1 up to and including n. Okay, and it might be worth bearing that in mind later. I'm sure there's one of the. I think there's one of the theorems that effectively says that n. I can't remember. We'll get to it anyway. That the number series n, uppercase n, is effectively equal to the system compounded of Zn and n0 primed. Okay, so what else have we got? The condition m is a part of Zn by 92 and 93 is obviously equivalent to each of the following conditions. So the conditions shown are from 93. So the m is not greater than n, m is less than n primed, and n0 is a part of m0. So these are all from 93. And what else have we got? 92 to express how that m is. Okay, so what was I going to say? M is a part of Zn. That means that by definition, m is less than or equal to n. As m is an element of Zn, then m is less than or equal to n, and vice versa by definition. So it's obvious that this condition is equivalent to m is less than or equal to n, or m is at most equal to n, which has been shown in theorem 93 to be equivalent to each of the other conditions. Okay, so there's really nothing to prove there anyway. Not really anyway, nothing substantial. Okay, so theorem 99. So we've got that 1 is an element of Zn and n is an element of Zn. So this is kind of obvious, and certainly the diagram that I've already drawn shows really how obvious this is, but it needs to be proved, right? We can't take it for granted. Just because I've drawn a diagram on the screen doesn't mean that it doesn't need proving. It does. So the proof follows from 98 or from 71 and 82. Okay, so kind of obvious from 98, I guess. But what's this with 71 and 82? I'm not sure. Actually, I've got some notes on this. Actually, I am going to have to refer to some. I've got some brief notes for this because there is a lot to get through. There is a lot to say. So you'll have to bear with me as well. By the way, I'm going to have to think quite carefully about some of the parts because it's not very complicated. The proofs of the theorems in here are not exactly complicated. It's just that sometimes you've got to look at them in just the right way. Okay, so what have I got for 99? So n0 is a part of n0. So obviously n is less than or equal to n by 93, by theorem 93. Oh yeah, that was right. So I was looking through this and I couldn't quite figure out how 71 and 82 were used. Let's see how I get on. So I've written some other notes down. So n is not greater than n. It's kind of obvious, right? But n is not greater than n. Therefore, n is, of course, in Zn by definition. Also, if n and 1 are different, so n different from 1, then either, and this is by 88, either the chain of n is a part of the chain of 1, or the chain of 1 is a part of the chain of n. But the chain of 1, because n is different from 1, the only number chain that contains 1 is this chain, which is n, which is equal to uppercase n. So we can't have, therefore, that the number chain corresponding to 1 is a part of the number chain corresponding to n. So we've got the number chain of n is a part of the number chain corresponding to 1. So by 93, this says that 1 is less than is not great, is at most equal to n, or is not greater than n, and therefore by definition this means that 1 is a part of Zn, which is what we needed to prove for theorem 99. Okay, so I don't really know when it's so Dedekind says the proof follows from 98, and it is almost immediate from 98. I've used 88 and 79, I think, in my proof. I'm not really seeing it right now, how 71 and 82. I'm sure it's right, it's just I can't see it right now, how 71 and 82 go together to prove theorem 99. Anyway, that's enough of that. If anybody else can see how they how those two can be used to prove 99, I'm sure it's right, it's just I can't see it right now. Okay, so theorem 100. Each of the following conditions is equivalent, I would imagine that means to say, is equivalent by 98. Okay, so these three conditions are just by 93. And then we've already seen in 98 that these three conditions are equivalent to this condition. But now we've got another new condition, which is that Zm is a part of Zn. So all of these four conditions are also equivalent to this new condition. So we need to prove this in both directions. Okay, so if m is a part of Zn, then by definition m is at least at most equal to n, and if L is an element of Zm and L is at most equal to m, by 95, which was effectively kind of transitivity, then we get L is at most equal to n. Okay, so that follows from 95. So therefore, by definition 98, yeah, L is is an element in Zn. So because L was an arbitrary element of Zm, what we've shown here is that every element of Zm is an element in Zn, and therefore by definition 3 or whatever, we've got that Zm is a part of Zn. So we've proved that these four conditions, and in particular, these four conditions imply that Zm is a part of Zn. We now need to prove in the other direction. Conversely, if Zm is a part of Zn, so that's the assumption now. So assume that Zm is a part of Zn. Then by 7 must also M be a part of Zn. Okay, so that's because we know that M is a part of Zm. So that's from theorem 99. And because Zm is a part of Zn, the system Zm is a part of the system Zn, then using theorem 7, again, it's kind of a transitivity, then we get that M is a part of Zn, which is equivalent to this condition here. Okay, so that's what we needed to prove. Okay, so on to theorem 101. So just while I'm clearing the screen here, I'd be really grateful if you would consider subscribing to the channel if you haven't already done so, and hit the like button, and don't forget to leave a nice comment in the comments section. If you do have any questions about anything that I say in this video, or any of my other videos for that matter, please feel free to ask any questions that you have in the comments section, or to get in touch with me directly. Okay, so theorem 101, the conditions for the cases lambda, mu, and nu in theorem 90 may also be put in the following forms. The proof follows immediately from 90, and we observe that. So the only thing that's changed here is in where was it? So the conditions in theorem 90 were lambda, mu, and nu. So in this case, we've got m equals n is equivalent to the chain of m is equal to the chain of n. M less than n is equivalent to the chain of n is a part of the chain of m not primed. And m greater than n is equivalent to the chain of m being part of the chain of n not primed. Okay, well, it's clear from if m is equal to n that Zm is going to be equal to Zn. Okay, there's not really much to say about that, to be honest with you. Okay, so in this case, in the case of mu, we've got n naught is a part of m naught primed, which by theorem 100 is equivalent to m less than n primed. Have I got that right? Okay, m is less than n primed, which in turn is equivalent to Zm. Something's not right here. Part of Zn. Oh, no, that's right. Yeah, that's equivalent to, no. n primed. I knew there was something wrong. Right, yeah. n primed is a part of Zn. So in other words, we can replace this condition with the equivalent condition Zn primed is a part of Zn, and playing the same game for nu, we get the other one, which is that Zn primed is a part of Zn. Okay, so we've got a new way of determining of two natural numbers, whether they're equal or which one is greater than the other. Okay, theorem 102. Z1 equals 1. For by 99, the base number 1 is contained in Z1. Yep, so we've got 1 is an element in Z1. While by 78, every number different from 1 is contained in the chain of 1. So remember, 78 says that n is equal to the system compounded of 1 and n primed. Well, n is, of course, 1, the chain corresponding to 1, and n primed is the transform chain of 1. And 1 is not in n primed. But the two together, 1 and n primed, form the whole of the number series. So every number that is not equal to 1 must be an element in n primed, which is 1 not primed. And by definition 98, remember that Zn contains all of those numbers which are not in n not primed. In particular, Z1 contains all of those numbers which are not in 1 not primed. And therefore, since that means that 1 is the only number that can be part of can be an element in Z1. So Z1 is equal to 1. Remember, I've said this a few times now, but when we've got a system of one element that contains one element, we identify that system with that one element. Okay, so theorem 103. By 98, n is equal to the system compounded of Zn and no. I mean, this is by definition, right? So n not primed contains a certain collection of a certain system of numbers. Zn is by definition the system of numbers that are not in n not primed. So a number is either in if it's not in n not primed, then it's in Zn, and if it's not in Zn, then it must be in n not primed, and this is by definition 98. So every number belongs into one or the other of these systems, and therefore putting these two systems together, we must end up with n. So that's straight from the definition, from definition 98. Okay, so theorem 104. N is the is equal to the community of Zn and the chain corresponding to n. So n is the only common element of the system, right? So n is a part of Zn. We know that. That's from theorem 99. We know that n is a part of its own chain. What was that? 50 something or other. Sorry, no, 70. Actually, I don't know. Well, it follows from one of the theorem 57 or something like that, I would imagine. Is it theorem 57? Oh, no, sorry, 45. Theorem 45. N will be a part of its own chain. So we've certainly got N in the community. So in G of Zn and N0, we've at least got N is an element of this. But are there any other elements? Well, because we know that N0 primed, let me get this right. Oh, sorry, N0. N0 is it? So this is theorem 77. Is equal to the system compounded of not M, N. N and N0 primed, where N is not an element of N0 primed. Therefore, for any number that is in the chain of N is either equal to N or it's an element of N0 primed. But remember that Zn contains all of those numbers which are not in N0 primed. In particular, Zn contains N, but it doesn't contain any elements of N0 primed. Okay, so therefore, we do have, in fact, that N is equal to. It's not just a part of the community of Zn and N0, it's actually equal to the community of Zn and N0. Okay. I mean, we could even... In fact, no, I'm going to leave it at that. I'm not going to risk tying myself in knots. Okay, so... Theorem 105, we're on to the next page now. Theorem 105, by 91 and 98, the number n primed is not contained in Zn. That follows immediately because we've proved that n is less than n primed, and Zn contains all of those elements, those numbers which are not greater than n. Well, n primed is greater than n, so therefore by definition cannot be an element of Zn. Theorem 106, if m is less than n, then Zm is a proper part of Zn, and conversely. So if m is less than n, then by 100, that's equivalent to Zm is a part of Zn. And since the number n by 99 is contained in Zn, and contained in Zn can by 98 not be contained in Zm. Why? Because Zm is all of the numbers that are not greater than m. Well, n is greater than m, and therefore n is not, so it's not an element of Zm. So n not in Zm by definition. So we've got that Zm is a part of Zn, but there are elements of Zn which are not contained in Zm, and therefore Zm must be a proper part of Zn. Conversely, if Zm is a proper part of Zn, then by 100, so Zm is a proper part of Zn, then it's Zm is a part of Zn, which is equivalent to m is less than m is at most equal to n. I'm trying to use Dedekind's terminology as much as possible. Since m cannot be equal to is proper parts. Conversely, right? Okay, so if Zm is a proper part of Zn, m cannot be equal to n. Right, okay, yeah, okay. So by theorem 101, if m was equal to n, it would follow that Zm is actually equal to Zn, but we've made the assumption that Zm is a proper part of Zn. So we can't reverse this. We can't get the other inclusion, so to speak. We can't obtain that. Because there are elements by assumption, there are elements of Zn which are not elements of Zm. So we can't have that m is equal to n, and therefore we must have that m is less than n, which is what was to be proved. Theorem 107, Zn is proper part of Zn primed, follows by what we've just proved. Because n is, of course, less than n primed. Nothing really to prove there. Okay, so theorem 108. So we want to prove that Zn primed is equal to the system compounded of Zn and n primed. So for every number contained in Zn primed by 98 is less than or equal to n primed, and hence either equal to n primed or less than n primed. And therefore by 98 is an element of Zn. Right, okay, so this contains all numbers m which are less than or equal to, or okay, I'm just going to keep saying less than or equal to. So that means that either m is equal to n primed or m is less than n primed. But if m is less than n primed by 93, any number less than n primed is by 93. What's 93 say? Yeah, so this is m is less than n primed is equivalent to m is less than or equal to n. So and therefore by 98 is an element of Zn. Therefore by 98 is an element. Right, okay, so yeah, if m, in the case when m is less than or equal to n, that means that m is going to be an element of Zn. So we can say then that any element of Zn primed is either an element of Zn or it's equal to n primed. Right? Any element of Zn primed must be less than or equal to n primed. So m is either equal to n primed or, as we've seen, m must be an element of Zn. And then conversely, by 107, Zn is a proper part of Zn primed, and by 99, n primed is an element of Zn primed. And then by 10, we have that the system. Right, okay, so Zn is a part of Zn primed, and also n primed is a part of Zn primed. So the system compounded of Zn and n primed must also be a part of, that's not equal to, that shouldn't be, that should just be parts. Zn primed is a part of that. The system compounded of Zn and n primed is a part of the system Zn primed. So then putting these two together using theorem 5, we get equality. And that proves theorem 108. Okay, so flying through these. Theorem 109. The transform Zn prime, so the transform chain, and no, sorry, it's not a chain. Just the transform. The transform of the system Zn is a proper part of the system Zn primed. So Zn primed is a part of. So obviously the primed in here, it's Zn, kind of imagine some brackets, all primed, and then the other one it's Z of the transform of n. Okay, so let's have a look at the proof of this. For every number contained in Z in here, in Zn all primed, is the transform n primed of a number contained. Right, okay, so since Zn all primed is the transform of the system Zn, that means that all elements in Zn primed are of the form m primed, where m is an element in Zn. Okay, so applying the transformation phi, presumably, then we get this kind of situation. So since m, by definition, in fact, not necessarily by definition, m is a part of, is an element of Zn, then we get by, what is it? 100, theorem 100, that this is equivalent to m is less than or equal to n. I need to change the page, don't I? Okay, so we've got, I'll continue on here. So I'm on to page 78. I'm on to the next page now, but I'll change it in a second. And hence by 94, m primed is less than or equal to n primed. So if we've got m less than or equal to n, hence by theorem 94, m primed is less than or equal to n primed. So if we think about what m is less than or equal to n means, it means that either m is equal to n or m is less than n. So obviously if m is equal to n, it follows that by similarity of the transformation phi, that m primed will be equal to n primed. In fact, you don't even need similarity for that, to be honest with you. If two elements are equal, then before transformation, then they're going to be equal after transformation. You don't really even need similarity for that. But then theorem 94, m less than n is equivalent to m primed less than n primed. So putting these two together, we get that m primed is less than or equal to n primed. So m primed less than or equal to n primed, that means that m primed, whatever m primed is, will be an element in Z sub n primed. Because m primed was an arbitrary element of Zn all primed, that means that Zn all primed is a part of Zn primed. That's by, sorry, write it a bit more clearly. So that's by definition 3, what it means for one system to be part of another system. Since further, the number 1 by 99 is contained in Zn primed. Yeah, so we proved that in theorem. Just let me double check. Yeah. One is an element of any of these systems of the form Z sub n, including Zn primed. But by 71 is not contained in the transform Zn all primed. So after the 1 can be transformed via this transformation phi, can be transformed into another number, but there is no number that transforms into 1. Okay, so 1 is in Z sub n primed, but it's not in Zn all primed. So because we've already shown that Zn all primed is a part of Z sub n primed, but therefore there is at least one element, 1, which is in Z sub n primed that is not in Zn primed, then that means that it's not just that Zn primed is a part of Z sub n primed, it's actually a proper part. Okay, so right, so we're on to theorem 110, and I need to change the page. Oh. I didn't really need to do that, did I? Delete all of that. Never mind. Okay, so theorem 110, Zn primed. So we want to prove that Zn primed is equal to the system compounded of 1 and Zn all primed. So in the previous proof, we showed that there is at least one number, 1, that is in Zn sub n primed, but is not in Zn all primed. Here, effectively, we're going to be showing that it's the only number. Okay, so we showed in the previous case that there is at least that one number, but now we're going to show that that's the only number as well. So every number of the system Z sub n primed different from 1 by 78 is the transform m primed of a number m, and this must be less than or equal to n. Okay, so why is that then? So every number m primed different from 1 in Z sub n primed must be less than or equal to n primed by definition. And therefore, m must be less than or equal to n. So where does that come from? Let me have a look. Theorem 94. Oh yeah, theorem 94 again. So either we've got n primed is equal to n primed, in which case this is by similarity. M is equal to n. Or we've got that m primed is less than n primed, in which case by theorem 94, this is equivalent to m is less than n. So putting these two together, we get that m is less than or equal to n. Hence by 98 must be contained in Zn. Okay, so all of these m's must be contained in Zn, because otherwise m would be greater, right? Because remember Zm or Z sub n is all of those numbers which are not greater than n, or at most equal to n. So all of these m's must be less, which are less than or equal to n, must be in Zn. Otherwise, we'd get a contradiction. Hence by because otherwise m would be greater than n, and hence by 94 also m primed greater than n primed, and consequently by 98 M primed would not be contained in Zn primed. So that's where we get our contradiction from. But from M is a part of Zn, then M primed is a part of Zn all primed. So, I mean, there's a couple of ways that we can justify that, I guess, but I guess the easiest way would be to refer to theorem 22. And hence, certainly, Z sub n primed, because this n primed here is arbitrary. What we've shown then is that any arbitrary element n primed of Zn primed that is not equal to 1 must also be in Zn primed, and therefore Zn primed can be quite confusing, can't it? Z sub n primed is a part of the system compounded of 1 and Zn primed. So we don't have equality because it may be the case. We have to account for the possibility that we haven't excluded yet that Zn primed may contain some elements which are not in Z sub n primed, or maybe something like that. Or this system compounded of these two, whatever. But that's what we're going to be excluding next. Since conversely, by 99, 1 is a part of Zn, I think there's a typo there. Where it says 1 is a part of Zn. Considering what Dedekind's using theorem 10, he's going to be using theorem 10. And for theorem 10, we really need... actually, no. Okay, it doesn't need to be Zn. Okay, I'll explain. That's probably the best thing to do. So let's clear some space. It could be a typo, but it's not actually forced to be. So we've got 1 is a part of Zn. Now, he doesn't say this here, but it has been proved in theorem 107 that Zn is also a part of Z sub n primed. And therefore, we have that 1 is a part of Zn primed. Actually, we've got 1 is a part of Zn primed from theorem 99 anyway. So we don't really need... I didn't really even need to state this. But considering that he's wanting to use theorem 10, we really need this here. That 1 is a part of Z sub n primed. And by 109, Zn all primed is a part of Zn primed. Then by theorem 10, we get that the system compounded of 1 and Zn all primed is a part of Z sub n primed. So then, putting this together with this, we get, and using theorem 5, we get equality. Okay, so definition 111. If in a system E of numbers there exists an element G, so presumably E doesn't have to be it doesn't have to be a number chain. It's just some collection of numbers, some arbitrary collection of numbers. There exists an element G which is greater than every other number contained in E. Then G is said to be the greatest number of the system E. And by 90, there can evidently be only one such greatest number in E. If a system consists of a single number, then is this number itself the greatest number of the system? Theorem 112 by 98, n is the greatest number of the system n. Okay, because Zn is the system of all numbers not greater than n. Okay, so therefore, by definition 111, n is the greatest number in Zn. Theorem 113, if there exists in E a greatest number G, so E here is clearly this system of numbers, this arbitrary system of numbers that was spoken about in definition 111. If there exists in E a greatest number G, then E is a part of ZG. Okay, so for every number contained in E is less than or equal to G. So every number in E is less than or equal to G, or not greater than G, whatever. And hence by 98 contained in ZG. Oh, easy peasy, right? Which was to be proved. So by definition, effectively, oh, we're on to the next page, aren't we? So that's follows straight from the definition 98. Okay, so theorem 114. How far I've got left to go? 2 pages, isn't there? Right. If E is a part of a system Zn, or what amounts to the same thing, there exists a number n. So, okay, 113. What amounts to the same thing by 113? E is a part of a system Zn. There exists a number n such that all numbers contained in E are less than or equal to n. Then E possesses a greatest number G. Okay, so the system of all numbers P satisfying the condition. So we've got the condition E is a part of ZP. And by our hypothesis, such numbers exist. Right, because by assumption, E is a part of a system Zn. Okay, so there is at least one number. There are such numbers for which this condition is satisfied. By our hypothesis, such numbers exist is a chain. So I've got some notes for this because it was a little bit confusing. Because by 107 and 7 it follows that E is a part of ZP primed. Okay, so E is a part of ZP. ZP is a part of ZP primed. So therefore E is a part of ZP primed. Follows that E is part of ZP primed. So, okay, so the series of numbers. So if K is the series of numbers, series of numbers. P, such that E is a part of ZP, then what we've shown is that P primed is also a part of K. Right, so K is the series of numbers P such that E is part of ZP, but we've shown that E is part of ZP primed, and therefore P primed, the transform of P, must also be a part of K. So therefore, K primed is a part of K, and therefore this series of numbers is a chain. by definition. So if it's a chain, it's a chain of numbers. It's a number chain. So by 87, there must be, so let me have a look at 87. In every number chain, there exists one, and by 84, only one number k, whose chain k0 is equal to k. So this chain of numbers, k, corresponds to the number g. So is effectively, we've effectively got k is equal to g0, where g signifies the least of these numbers. So that's from 96 and 97. 96. In every part t of n there exists, right, so k is a part of n, so there is a least number. Yeah, so 97, the least number in the chain. Right, the least number of the chain n0 is n. So the least number in the chain g0 is g. So g is the least number. In k, or in g0 or whatever. G signifies the least of these. Hence, also, E is a part of ZG, right? Because G is in this K. So E is a part of ZG. Therefore, by 98, every number contained in E is less than or equal to G. Okay? And so, right, okay, yeah. And we have only to show that the number G is itself contained in E. This is immediately obvious if G is equal to 1. Because remember, we don't deal with empty systems here. Right? So if G is equal to 1, then ZG is going to be equal to Z1. We've seen that Z1 is equal to 1. It's just got a single element. So that means that if E is a part of Z1, then E must be equal to Z1, and therefore E must be equal to 1, and therefore 1 is an element of E. We don't deal with empty systems here. So, and then by 102, ZG, and consequently also E consists of the single number 1. But if G is different from 1, so now we've got G different from 1. And consequently by 78, the transform f primed of a number f. So, okay, G is equal to f primed. So f primed is naturally the transform of a number f. Then by 108, E is a part of... Okay, so we've got E is a part of ZF, right, okay. So if E is a part of ZG, then E is a part of ZF primed, which by 108 is equal to the system compounded of ZF and F primed, which is G. If therefore G were not contained in E, then would E be contained, E be a part of ZF? Okay, so if G, this element here, is not actually in E, then we have that E is a part of ZF. And I think this is going to be a contradiction. And there would consequently be among the numbers P a number F, which is right, because remember K was the series of all numbers P such that E is a part of ZP, we found that G was the least element of that series of numbers. So, but now we've evidently, if we assume that G is not in E, then we get that E is actually a part of ZF, where F is a number that is less than G. So actually F would be in K, and G is not in fact the least number. So that's a contradiction, right? So the upshot is that G must be an element in E, which was to be proved. Okay. Right, onwards and upwards. Definition 115. If L is less than M and M is less than N, we say the number M lies between L and N, and also between N and L. Okay, theorem 116. Let me clear a little bit. In fact, no, I won't bother. So I'll be going on to the next page. So theorem 116, there exists no number lying between N and N primed. Okay, so I'll go on to the next page. For as soon as M is less than N primed, and hence by 93, M is less than or equal to N prime, so these two are equivalent statements, we cannot have N is less than M. Right, because this excludes it, right? So if we start with the assumption that M is less than N primed, what we're trying to prove, there is just no number line between, right. We start with the assumption M is less than N primed. This is equivalent to M is less than or equal to N, but that is the negation of N is less than M. Okay, so this can't happen. So we must have that M is less than or equal to N. So in particular, if we replace M with N, we've already proved that N is less than N primed in theorem 91 or something like that. So therefore, we can't have any number between N and N primed. Theorem 117. Let me clear a little bit of space. Okay, theorem 117. If T is a number in uppercase T, but not the least, then there exists in uppercase T one and only one next less number S, i.e. a number S such that S is less than T, and that there exists in uppercase T no number lying between lowercase s and lowercase t. So T is not necessarily a part of N here, by the way. We may take T to be a part of N, but it's not forced to be. There might be other elements of T which are not numbers. At least I can't see any reason why we specifically need to assume that T is absolutely a part of the number series. Similarly, if lowercase t is not the greatest number in uppercase T, there always exists in uppercase T one and only one next greater number u, lowercase u, i.e. a number lowercase u such that lowercase t is less than lowercase u, and that there exists in uppercase T no number lying between lowercase t and lowercase u. At the same time, in uppercase T, lowercase t is next greater than s and next less than lowercase u. So proof. If lowercase t is not the least number in T, so lowercase t is not the least number in T, then let E be the system of all those numbers of T that are less than T. So E is the system of numbers of T that are less than T. Then by 98, E is a part of said T. What does 98 say? Oh, yeah, of course, yeah. And hence by 114, there exists in E a greatest number S. So S is the greatest number of E, obviously possessing the properties stated in the theorem. And also, it is the only such number. So S is the greatest number of E. So evidently must also be must be the least number of T. Okay, so because T is not the least number in uppercase T, so lowercase t is not the least number in uppercase T, that means that there are numbers that are less than T, less than lowercase t in uppercase T. So that means E and T, they're not kind of, they've got an overlap. They've got common elements, common numbers in this case. And S is one of those numbers. So S is the greatest number of E. There's a number S. Next, so T is a number in T. So what were the conditions of the theorem? The properties stated in the theorem. No number lying between S and T is a number in T, but not the least. So, S must be, S is obviously less than T because it was in E, but it's the next least number from T, because if there was another number between, there can't be another number between S and T. If there was, let's say, what shall I call it, R, this would be a contradiction, right? Because then S is, R would necessarily be in the system E, but we've already established that S is the greatest number in E, but now evidently we've found a greater number. So in other words, there can't be any numbers between S and T. So S must be the next least number from T. If further T is not the greatest number in uppercase T, then by 96, there certainly exists among all the numbers of T that are greater than T a least number U, which and which alone possesses. So this was that every part of the number series has a least number. 96. Yeah, so that's kind of the well ordering principle. Dedekind doesn't use that, but that's effectively what 96 is talking about. So it's a similar kind of argument. So we've got a system of all of those numbers which are strictly greater than T. There must be a least number U, and there can't be anything between T and U. Okay, there can't be any number T, V, U, for example, because then V would necessarily have to be in this system of numbers greater than T, lowercase t. But it's a number that is less than apparently the least number, so that would be a contradiction. So U is the next number following T. Again, this system and the system uppercase T don't have to be mutually exclusive or disjoint, or however you want to refer to it. In like manner, the correctness of the last part of the theorem is obvious. And then theorem 118, just to finish things off, in uppercase N, the number N primed is next greater than N, and N next less than N prime. So the proof follows from 116 and 117. Okay, so there's nothing really for me to say about that. So that brings us to the end of this chapter. So that's it. It's been quite a long one. It's been a difficult one for me to get through, actually. Quite a lot to keep track of. So the next chapter, chapter 8, is quite a short one, but it's quite an important one also. In fact, the next 3 are a little bit more tricky in certain respects. They're relatively short. Chapter 9, I probably won't go through absolutely everything. So there are a couple of lengthy remarks towards the end of chapter 9 that I'm probably not going to go into in too much detail. I'm really going to concentrate on the main theorems and their proofs. So they're quite short chapters, but they are really important, and they are a bit more challenging in certain respects than the chapters that the theorems that we've seen up to now. They've been relatively straightforward, but in the next few chapters, some of the theorems they're still quite straightforward, but you just got to think about them a little bit more, and their proofs and things like that. So that'll be for the next video. So thank you for watching this video. If you made it to the end, don't forget to subscribe to the channel, hit the like button, and let me know if you've got any ideas about any other works that you'd like me to take a look at and make some videos about on my channel. So once again, thank you for watching, and I will look forward to seeing you in the next video.